Well friends, let us resume our discussion on thermal system modeling. Last time I gave you basic equations and its an electrical analog was also given of a typical thermal system. Well, I think the revision of those equations will come now through a systematic example in which the resistance, capacitance elements will be visible. I take the example of a tank. Let us say I take this as the tank. This is the input and here is the output. The liquid flowing in is at the rate Q and the liquid flowing out is also assumed to be at the rate Q, so that there is no change in the hold up of the tank. The volume of the tank remains the same. In this particular case, as you know that the entire volume of the tank will not be at a uniform temperature, so I use a stirrer, so that using appropriate stirring I assume that the temperature of the liquid in the tank is uniform and can be represented by a single temperature. You will please note this point, that this stirring is giving us the sufficient reasoning to assume the temperature of the tank to be uniform. Of course, it is an assumption, otherwise you would have got a distributed parameter system model and we are heading towards a lumped parameter system model. This particular type of system in process industry in the short form is referred to as CSTR, continuously stirred tank reactor. It is the standard name used there, a CSTR, I repeat, continuously stirred tank reactor. Okay? So, in this case we have taken Q. Let me take the units. Q is in meter cube per second, the rate of flow of the liquid in the tank. Let me assume that this liquid is entering at a temperature theta I bar plus theta I. You will note that the two theta I bar and theta I have taken. Theta I bar is the steady state temperature, that is the temperature corresponding to nominal operation of the system, and theta I is a deviation with respect to steady state temperature. It is a perturbation in the system, maybe an uncontrolled perturbation, and you want to study the effect of this perturbation on the dynamics of the system. This will become my standard symbol, you see, that is I will be representing a steady state and a perturbation. Steady state corresponds to nominal operation of the system. Okay? So, I assume that the input conditions correspond to Q, a constant flow rate, and a temperature theta I bar plus theta I, the units being degrees centigrade. Okay. Now, let us say what is the process. In this particular case, it is a heating process and I take up the situation where the heating is going on through a heater. This is the heater element and through this heater the heating is going on. So, naturally this you will say is the heat given to the liquid, and again as per the terminology used earlier, I will be using H bar plus H. You have to very carefully note this point. H bar is the steady state heat flow rate, the units of heat flow being joules per second, and H is the perturbation in the heat flow rate, which in this case may be a controlled perturbation. Maybe the objective of the system is this, that when theta I, which is uncontrolled, takes place, you will like to control small h, so that the effect of theta I is reduced to 0 or reduced to a negligible value. So, you may say that H is also a perturbation, but it could be or it will be a controlled perturbation to filter out the effects of disturbances acting on the system. Okay? Joules per second here, please note. So, it means this particular liquid which is being heated using a heater. Now, this exit has got the flow Q and I assume that the heater temperature here is theta 1. Let me say again theta 1 bar plus theta 1. Theta 1 bar is the steady state value and theta 1 is the variation from the with respect to the steady state value. This is your heater mass. Now, as far as the liquid in the tank is concerned, I assume that its temperature is theta 2 bar plus theta 2. So, it means exit temperature is theta 2 bar plus theta 2, assuming that there is no change and uniformity of the temperature has been assumed. This is the exit condition, this is the condition within the tank, this is the inlet condition and this is the heater position. And the purpose is to write the dynamical model for this particular system. In addition to this, let me take one more variable here, and that variable is that this particular tank wall is definitely radiating energy, is definitely giving energy, thermal energy to the environment, and let me assume that the environment temperature is theta A bar plus theta A. Again, theta A bar will be the nominal environmental temperature at the time when the total system operation was at steady state, and theta A is a variation in the environmental temperature itself, which is beyond your control. Okay? So, this is the total situation, and you will help me now. We will apply the basic equations I gave you last time on this particular model, on this particular system, and write systematically the dynamical equations of the system. You will keep in mind that theta I is a disturbance for me, theta A is a disturbance for me, and small h is the controlled variable. When I design a feedback control system for this particular situation, I will really control this h in such a way that the effects of theta I and theta A are reduced to 0. This is the objective of the system. The control system is to come later. At this particular juncture, the objective is to study the dynamical model of this thermal plant or the temperature process, you call it. Okay. Equations. I will start with the heater equations. Okay. Heat balance for the heater. Help me please. The input, storage and the output conditions you have to tell me. Let me first see what is the input condition. The heat input, yes, you can say as far as the heater is concerned, H bar plus H is the total heat which electrical energy is creating. Now, this particular heat, well, electrical units I will convert to heat units later, but let us say H bar plus H is the heat produced. Because of the electrical energy supplied to the heater, H bar plus H is the heat produced. Now, where is this heat going? This heat, number 1, is part of it is getting stored in the heater mass itself, and part of it is going to the liquid in the tank. Is it all right, please? The part of it which is stored in the heater is given by, let us say, m is the mass of the heater, and let me take it the units as kilogram. Here it is a more or less revision of the basic laws also through this example. M is the mass of the heater and C I take as the specific heat of the heater substance. Let me take the units of C as joules per kilogram degree centigrade. Okay. Now, you tell me what is the rate of heat storage in the heater. The rate should come in terms of joules per second. You will please note that the rate of heat storage in the heater will be given by mc d theta 1 by dt, where theta 1 is the heater temperature. You can look at the units. Joules, this is kilogram, into joules per kilogram degree centigrade into degree centigrade per second is equal to joules per second. It is the rate of heat storage in the heater. I hope this is okay. Now, how about the other component, that is the rate at which the heat is being given to the liquid. And as you will see in this particular case, the heat is going to the liquid through a convective process. This is a solid liquid interface over here, solid liquid interface, and through the convective process the heat is being given to this particular liquid. Now, again at this particular point the equation can be written as the theta 1 is the temperature of the heater, theta 2 is the temperature of the liquid mass, and therefore the rate at which the heat is being given to the liquid is UA into theta 1 minus theta 2. Recall the units A in meter square and U is the film coefficient. The film coefficient at the liquid solid interface. Yes, what should be the units please? Joules per meter square, degree centigrade, seconds. You can see that this is the units, this is for this particular U, I have written this, the unit says joules per meter square, degree centigrade, seconds. Now you please see that UA theta 1 minus theta 2 will turn out to be in joules per second. This is the rate at which the heat through convection process is going to the liquid in the tank. Come on now, with this information, if there is any question you are welcome to raise it here. Otherwise, with this information I write the heat balance equation. The heat balance equation will be mc d theta by dt. The rate at which the heat is being stored into the heater mass is equal to the rate at which the heat is coming into the heater mass. It is, yes, what is the value? H is the rate coming, the rate at which the heat is coming into the heater mass minus the rate at which it is going out. It will become theta 1 minus theta 2 into UA. This becomes your heat balance equation. Okay. You will note one point, let me explain it here, that I have not taken the theta bar terms. The total equation, if I want to write, will look like this: mc d by dt of theta bar plus theta, sorry, theta 1 here, theta 1 bar plus theta 1 is equal to h bar plus h minus theta 1 bar plus theta 1 minus theta 2 bar plus theta 2. This is the total equation. You may please note, I have directly written the perturbation model, but let me explain how the perturbation model has come. This is the total equation. Theta 1 bar plus theta 1 is the total temperature at any time t as far as the heater mass is concerned. H bar plus H is the total heat generated in the heater. Theta 1 bar plus theta 1 the heater temperature, theta 2 bar plus theta 2 is the liquid temperature. Now if I break this equation in two parts, at the steady state you find d by dt theta 1 bar is equal to 0. So help me please, what is the equation at steady state? I can write the equation at steady state as h bar equal to yes into UA, you are right please, UA into theta 1 bar minus theta 2 bar. Is it okay please? This is my steady state equation, all of you please note, because the derivative will become 0, theta 1 bar being a constant, the derivative will become 0, and at steady state the left hand side is equal to 0, and from the right hand side I write h bar is equal to UA theta 1 bar minus theta 2 bar. It means if there is no disturbance acting on the system, if there is no variation in the various temperatures which are there as far as the system the thermal system is concerned, then at steady state the heater mass balance is given by h bar, the heat produced, is equal to UA theta 1 bar minus theta 2 bar. Now coming to the perturbation model, I am using the steady state balance and the perturbation model separately. Coming to the perturbation model, from this equation I write mc d theta 1 by dt equal to h minus theta 1 minus theta 2 into UA. This becomes my equation, and if you understand this situation please, now onwards I may not write the steady state balance again and again, assuming that with respect to steady state the input, the energy conditions will be satisfied. My specific objective is to take the perturbation, because if there is no perturbation there is no need of a control system. The need of a control system arises if and only if disturbances act on the system, and these disturbances will deviate the various variables from the nominal point, and that is why the need for controlling these disturbances arises. I hope this is okay. Under steady state open loop system will work and closed loop system or feedback system is not needed, and therefore the steady state model need not be written again and again, we will directly write the perturbation model henceforth. Okay. Now, this particular equation, if you say, if I assume that temperature degree centigrade is analogous to voltage volts, heat joules per second is analogous to current amps. Can you help me please? What is the equivalent electrical equation for this system? I hope it will come easily. Come on please. In this particular case, if degree centigrade volts joules per second amps relationship is taken, I will write it directly and wait for questions from you if necessary. You see that C d theta 1 by dt, let me call it C1 dt is equal to H minus theta 1 minus theta 2 divided by R1, where let me call C1 as the thermal capacitance of the system and R1 as thermal resistance of the system. And now onwards, if you understand this point, I need not take up these variables in terms of mass, specific heat, film coefficient, area and all that. I assume that given a particular situation, I will be able to get the values of thermal capacitance and thermal resistance, and therefore the dynamical equations now onwards could be written directly in terms of C's and R's, if this point is very well taken here. You will please note that the identical equation is C dE by dt is equal to current source minus potential difference divided by resistance. This is your equivalent electrical analog. And in terms of electrical analog, for the thermal systems, I will be writing the thermal capacitance and thermal resistance as the parameters of the system, instead of going to the parameters M, C, U, A and other parameters again and again. This becomes the first dynamical equation as far as this thermal system is concerned. I hope this is okay up to this stage. If this is okay, I like to go to the second equation. What is the second equation? The second equation is given by the fluid or the liquid in the tank itself, because the same situation as you have seen in the case of a heater applies to the liquid. It stores energy, there is an input of energy and there is an output of energy, and I am going to write the heat balance for the liquid in the tank. Now here also you have to help me please. First help me for the storage of thermal energy. This last time also you had given me storage of thermal energy, the liquid now I am taking in the tank, rate of energy storage will be given by, yes, what is the total mass? V, the volume. The volume as you see will remain constant because the inflow rate has been assumed to be equal to outflow rate. So the volume of the liquid in the tank is a constant parameter. So V the volume, rho the density, units you can take meter cube, kilograms per meter cube, and of course if I multiply it by specific heat, V rho C becomes equivalent to MC, and V rho C d theta 2 by dt, the units will turn out to be joules per second, and it is the rate of heat storage in the tank. Okay? And now I hope you won't mind if I write this as directly C2 d theta 2 by dt, where C2 is the thermal capacitance of the tank liquid. Thermal capacitance of the tank liquid, the equation being I is equal to C dE by dt, E is the voltage, C is the capacitance and I is the current. You see that joules per second or the rate of heat flow has been taken as equivalent to current. Okay? I hope this C2 variable is all right for you now, and it is coming in terms of the parameters, the volume, the density and the specific heat. Okay? Now help me for the heat input and output. Yes, what is the heat input please? Look at the tank situation and let us see what are the sources of heat input. Yes. Heat input in this particular case, as you see, is through this particular heater. Any other source please? the inlet or the inflowing liquid is also a source of heat, because any variation in the tank, you see at steady state certain amount of heat is going on along with this liquid, but if there is a variation in the temperature, naturally there will be a variation in the heat carried by this liquid, and therefore there is going to be a variation in the heat input to the tank through this particular source. So, I will say, though it is a disturbance for the system with respect to the nominal point, I will say that there is a heat inflow from this source, there is a heat inflow from this source, and where is the heat outflow? The heat outflow will be here as well as here, that is through the environment. So, help me please now, what is the heat inflow? Look at this now, at this point Q is the Q meter squared per second, Q meter squared per second, rho is the density, becomes kilograms per second, into specific heat C into theta I. Note that I am not directly writing the perturbation variable, I will save my effort and I will avoid writing theta I bar again and again. Otherwise, theta I bar equations I will simply take out from the total equation and get the perturbation model. So, here I am writing theta I. So, it means it is the variation or perturbation in the heat flow rate, and units will turn out to be joules per second. This is the heat flow rate from this particular inlet point. And how about the heat flow rate from here? The heat flow rate from here is going to be, yes, theta 1 minus theta 2 into UA. This is the source, this we have already seen. This is the heat given to the liquid, it is the input for the liquid, it was output for the heater mass, becomes input for the liquid naturally. Okay? This is as far as the heat flow rate of this is concerned, liquid is from the heater to this source is concerned. Coming to this now, what is the heat carried away by the outflowing liquid? Is it not identical? Q rho C theta 2 joules per second. It is the heat carried away by the outflowing liquid. And lastly, let us see what is the heat lost to the environment. Here you help me, what is the heat lost to the environment? Well, there could be some storage of heat in the tank walls. Well, certain approximations are to be made, and let me make an approximation that the heat storage of the tank walls is negligible, and I assume the tank walls to be at the temperature theta 2 itself. If that is the case, then you please see, because of this particular interface between the solid mass of the tank wall and the fluid which is the air, again I may say that through the convective process the heat flow is taking place from the tank wall to the environment. It is the convective process, because the tank wall gives you the fluid solid interface, and U the film coefficient for that will come, A the area of cross section will come, and therefore, between theta 2 and theta A there will be a flow of heat. Now, if you see that Q rho C theta I and Q rho C theta 2, these are the terms which give the heat carried away through the liquid, and therefore, now I can write the heat balance equation. What is the heat balance equation? V rho C d theta 2 by dt, the rate of heat storage, the perturbation, I am again repeating, it is the perturbation in the heat storage, it will be joules per second. This is equal to the source. The sources are going to be Q rho C theta I plus theta 1 minus theta 2 U A minus Q rho C theta 2 minus, it is going to be theta 2 minus theta A into, let me say, just to make it different from U A, let me make it U 1 A 1 or U A or U 1 A 1 is all right, there is no problem. U 1 is the film coefficient at the wall air interface, and A 1 is the area of the contact, the surface area. Is it okay please? This could be written as you see, Q rho C theta I minus theta 2 plus theta 1 minus theta 2 as u a minus theta 2 minus theta a as u1 a1 into u1 a1. Is it okay? Now, let us go to an equivalent electrical parameters. If I take equivalent electrical parameters, I will write this equation as C2, the thermal capacitance of the liquid in the tank, d theta 2 by dt equal to theta 1 minus theta 2 by R1 is the thermal resistance of the heater mass, plus theta I minus theta 2 into R2 thermal resistance of the inflowing of the liquid in the tank, that is R2 is equal to how much? 1 over q rho c. It is I think obvious. R2, the thermal resistance, is equal to 1 over q rho c minus, let me put it, theta 2 minus theta a divided by R3. It is the convective thermal resistance at the air wall interface. So, if we forget about the basic parameters of the system and concentrate on R1, R2, R3 and C2, I think, well, it should not create any confusion, rather it should give a simplified version in terms of time constants, as you will see in terms of dynamical equations which we are going to write. So, from here this point onwards I will take these parameters only, and let me summarize my equations. C1 d theta 1 by dt equal to h minus theta 1 minus theta 2 by R1, C2 d theta 2 by dt equal to theta 1 minus theta 2 by R1 plus theta I minus theta 2 by R2 minus theta 2 minus theta a by R3. These are the two equations and hence the dynamical model. I will say the effort I wanted to put in to obtain the two differential equations has been obtained. It is a second order system because there are two differential equations involved. Now, you please see that as far as this system is concerned, if you want to write the state variable model, the equations are more or less in the state variable format, because you could take x1 is equal to theta 1 and x2 is equal to theta 2 as the two state variables, and you have got the equations in the form you want for the state variable formulation. It is x1 dot equal to, in this side you will write, you will please note what are the input variables in this particular case. H is an input variable which is a controlled input variable, theta I is an input variable, it is a disturbance input variable, theta a is also an input variable. So, in this particular case there are three input variables h, theta I and theta a, and two state variables theta 1 and theta 2. Okay? This structure should be seen. Now, if I ask you to give me a transfer function model, what will you say? You will have to first ask a question as to transfer function. For the transfer function, what attribute of the system I am interested in? Maybe I am interested in theta 2 as the output variable and h as the input variable. In that particular case, I will get the transfer function between theta 2 and h, assuming theta I and theta a to be 0. This point is to be noted, please. As far as the state variable model is concerned, x1 is equal to theta 1, x2 is equal to theta 2, input variable r is equal to h, it is a vector now, h, theta I and theta a. These are the input variables. If you are interested in a transfer function model, take one input at a time. Say I am taking h. So, I will let theta I and theta a go to 0, because I am interested in the study of the dynamics of the system through transfer function being input output formulation. You will have to take one output and one input. Taking theta 2 as the output, h as the input, theta I and theta a equal to 0, I will eliminate theta 1 and get a transfer function model between theta 2 and h. Identically, if you are interested to study from the input output model the effect of the disturbance variables, in that case the reference input or the controlled input will be assumed to be equal to 0, and you will set up a mathematical model between theta I and theta 2 or theta A and theta 2 as the study demands. Okay? And I can leave this exercise to you, that this type of manipulation you should be able to do to get the required formulation either in the transfer function model or in the state variable format. Okay? Now, let me take a particular case which I will be using later as a case study for a control system. It is a simplified version of this. I assume that the heat storage, please note this point and modify your equations, heat storage in heater mass is negligible compared to the heat storage of the liquid. Heat storage in the heater mass I am neglecting. This is the based on this assumption, I want to set up a mathematical model here, a plant model, and I will like you to store that model in your memory, because I will recall that from your memory when I take a control system. Okay? And for that I will like you to have a look at this particular model itself. If you take the heat storage is equal to 0, in that particular case please see the equation 1 gets modified to, the left hand side becomes equal to 0, it gets modified to H, the controlled heat, is equal to theta 1 minus theta 2 by R1. Under this assumption this becomes your equation, H is equal to theta 1 minus theta 2 by R1. How about the second equation please? I want you to give me the second equation. The second equation under this assumption, first equation let me write it, H is equal to theta 1 minus theta 2 by R1, and the second equation will turn out to be C2 d theta 2 by dt equal to, now I can replace this by H, the input variable, theta 1 minus theta 2 by R1 plus theta I minus theta 2 by R2 minus theta 2 minus theta A by R3. This becomes our equation. I like to rewrite this equation neatly. This very equation now becomes C2 d theta 2 by dt equal to H plus theta 1 minus theta 2, theta I sorry, minus theta 2 by R2 minus theta 2 minus theta A by R3. I hope this is okay. This becomes a single equation, and in the process please note I have reduced the second order system to a first order system. Naturally the order of the system depends upon the number of energy storage elements. In the earlier situation there were two energy storage elements, the heater mass and the liquid in the tank. If I assume that the heater mass energy storage is negligible, then by physical reasoning also you can say that the system now is a first order system, and it is amply demonstrated by the corresponding mathematical model, which turns out to be a first order differential equation and hence a first order state variable model. Okay? So, in this particular case now this is the model, this is the equation, and this equation can be rewritten in the form C2 d theta 2 by dt equal to H minus, please see little manipulation here, 1 by R2 plus 1 by R3 into theta 2. Okay? I need your attention here because I am going to put it in a format which I will be extensively using later. You will recall what is the personality of a first order system. The personality of a first order system we had said depends on the system gain and the time constant. This being a first order system, I will like to bring this in the standard form, that is somehow I want to relate the system gain and the time constant in terms of the system parameters, and this is what I am going to do in terms of little manipulation on this equation. So, for that what I am doing is this H I have written here, theta 2 is taken and all these the terms, the coefficients of theta 2 have been assembled. Look at the other terms. The other terms are plus theta I by r2 and plus theta a by r2. Is it okay, please? This I could write as equal to h minus. Could I write this as 1 over r, some new variable r naught, no new parameter. R naught is a parallel combination of r2 and r3. So, minus 1 over r naught theta 2 plus theta I over r2 plus theta a over r3. This let me modify r3. You see that in electrical circuit, resistance into capacitance is the time constant and its units always is seconds. Now, in thermal systems identically, a little exercise for you. Look at the units of thermal capacitance and the units of thermal resistance. You will find that the units of capacitance into resistance will turn out to be seconds, and therefore, equivalent to electrical systems, C into R will turn out to be the units in seconds, and I will call it as the time constant of the thermal system. So, what I do in this case, I take this term on this side C2, or can I write it directly in Laplace domain? That will be helpful. SC2 plus 1 over R naught theta 2s equal to 1 over R2 theta is plus 1 over R3 theta as plus Hs. Hs is the Laplace transform of small ht, that is the controlled variable. This is in the Laplace domain. Now, putting this equation in this format, I write S R naught C2 plus 1, okay, theta 2s, but let me take it divided by R naught, yes, equal to 1 over R2 theta is plus 1 over R3 theta as and plus Hs. This becomes the equation. And now, let us define the variables which describe a first order system. I take tau is equal to R naught C2. It is the time constant of the thermal tank, and the units, as I said, you should really verify the units of tau will turn out to be seconds. So, in this particular case, what I am doing is I am writing this equation in this form: output theta 2s is equal to some constant k into tau s plus 1 Hs plus some constant k d1 over tau s plus 1 theta is plus some constant k d2 over tau s plus 1 theta as. I hope this will be all right. Make an attempt, please. Some suitable constants k, kd1 and kd2 I define, and in terms of these constants this becomes my equation. Theta 2 is the output variable, Hs is the controlled variable, theta is and theta as are the disturbance variables. Okay? Well, suitably in the form of a block diagram, if I take, and this is the block diagram I will like you to recall when I take a control system around this plant. What is the input to the system? It is Hs. What is the plant model? It is k over tau s plus 1. What are the disturbances acting on the system? The output of the system is theta 2s. This is your plant system as far as input output variables are concerned without disturbances. You can see this is your plant model. If you take your disturbances to be 0, this becomes the plant model. And if you are writing a model between theta is and theta 2s, k d1, yes, it is k d1, tau s plus 1, it is theta 2s variable here, theta 2s variable here, k d1 tau s plus 1, and theta as variable if I take, because all of them are inputs, k d2 over tau s plus 1, and this is my theta 2s variables here. So, look, you see, these are the 3 models, input output models in terms of the output variable of interest and the 3 input variables of interest to me, because I will like to study the effects of disturbances on the process. Now, instead of putting the models this way, I will like to club all the 3 into a single transfer function model, and for that I can make a diagram like this. You help me if I make an error. H s is the input, let me put the system gain k here, a summing point here, and let me take a summing point here as well. Let me take here as k d2. It is for you to see that the 3 block diagrams I have given are being now put in a single block diagram. This I put as k d1. With k d1 I have got the variable theta I, with k d2 I have got the variable theta a, and here I put 1 over tau s plus 1 block, and this becomes my theta 2s. Please see whether this is okay. This is the input output relationship. Now, from this you get between theta 2 and h, setting theta I and theta a equal to 0, naturally whatever we have written we are getting. Similarly, setting these 2 variables 0, you have got the transfer function between theta 2 and theta I, and identically the third transfer function. So, this is my summing block. It is a symbolic representation of the additive effect which is going on in the process, and these 3 input variables in this particular block diagram have been explicitly shown, and this is the output variable theta 2. Okay. This becomes the total block diagram of the system, and as I said that this becomes the plant model of the system, where the input, any plant model I will say is complete for the study of control systems if you give me the controlled variable, that is the manipulated variable which finally your controller will activate, and the disturbance variables as the input, and the particular attribute of interest as the output, and it is well connected by suitable dynamical blocks, the transfer function blocks, that is the plant model. Okay. Well, I do not think the liquid level systems I had envisaged for this today's discussion we can take today, but one point I will like to take here today itself, because it is in continuation, and that point is regarding the sensing of the variables. I need your attention please, a very important point from the point of view of process applications, extremely important I will say. Sensing. Now, you see that if I want to control this h, the controlled variable, to nullify the effects of disturbances, I will require a feedback loop, and the feedback loop will require the sensing of the controlled variable or the output variable. What is the controlled variable? The controlled variable is of course theta 2. So, if I put my sensor here, I need your attention please. In that particular case, what will happen? My sensor, let us say thermocouple. The thermocouple output you know is in millivolts, very small voltage. Now, if the stirring here, vigorous mechanical motion of the liquid is going on, because of the vibrational effects, the noise signals will be produced, and these noise signals will be high frequency signals. Note my point please. And therefore, if a sensor is placed over here, in that particular case, in addition to the useful information, that is a voltage proportional to the controlled temperature, the noise signal will also be going in the feedback loop, through the feedback loop into the plant, and the noise may even dominate the useful signal, and therefore the control action will not be the way you want it to happen. So, what are the alternatives? One alternative, one way is this, that instead of installing the sensor over here, you install this particular sensor a little away, let us say at this particular point, so that the effect of thermal agitation, so that the effect of vibrations is reduced, if not eliminated completely. Electrical filters of course can be used, but why to first create noise and then filter it? It is better first to avoid noise signal right in the beginning, and to avoid noise signal, the sensor instead of this particular point may be put at this particular, and this is what is normally happening in the process industry. Now you will note that if you put a sensor here, your mathematical model which you have derived, the plant model which I have stored in your memory will change. The reason being, now in this particular case the controlled variable is not theta 2, but the controlled variable is this quantity, because controlled variable is actually that variable which you are sensing. Anything is happening to the system is unknown to you. The variable which you are sensing and feeding back in the control loop, as far as the controller is concerned, the controller does not have any information at this particular point. The controller has information of the temperature at this point only. So the controller is intelligent with respect to this information and not with respect to this information. So it means in this particular case, for the purpose of control system design, if you are setting up a control system model, a plant model, in that particular case the output variable should be this temperature and not this temperature. Let me say that this temperature is theta only, let us say theta, let me use this variable for this, this temperature is theta. So little change in your model, but very important change. You have to now tell me what is the relationship between theta and theta 2, and from that relationship, using that relationship I will modify my earlier model and will get the overall system model. Yes, can you help me please? What is the relationship between theta and theta 2? Assuming that this particular length is L, this particular length is L, and the liquid is moving with a velocity v, how much time will it take for the liquid to move from this point to this point? L in meters, v in meters per second, L in meters and v in meters per second please. How much time will it take? L by v seconds, okay. And what is v? V, let me write it here, is equal to q is the meters cube per second, q divided by area of cross section of this pipe, meter square. If I take v is equal to q by a, meter cube divided by meter squared per second, meter cube per second divided by meter squared, I have got v in meters per second. This becomes the velocity. If this velocity the liquid is moving and it has to move a distance L, in that particular case the time taken is L by v, and let me use the symbol tau d. I am reserving it for throughout the course. The tau d, the delay time, or in the literature it is also referred to as the transportation lag. I will like you to really get these terms very clearly. Dead time, because this is the dead time, the name, the nomenclature is obvious. This is the time which the system is not using. Delay time, transportation lag. Ideally you would like that such a thing should not happen, transportation lag. In that particular case your model turns out to be theta t is equal to, please see, theta 2 t minus tau d. This becomes your model. A minute more please. Theta t is equal to theta 2 t minus tau d becomes your transportation model. And in Laplace domain, theta s, help me please, what is the Laplace transform of this? E to the power of minus s tau d theta 2 s. This is your standard Laplace operator, let me not explain it. This is time shift operator. Theta s is equal to e to the power of minus s tau d theta 2 s. So it means e to the power of minus s tau d becomes the transfer function of the delay element, if you call it. It is not a physical separate element, it is a phenomenon taking place, but in the term of, in the form of a block diagram I can take it as a dead time element in the system. This is the transfer function of the dead time element in the system. Okay. Now, please see what will become your transfer function model if I take this as theta 2. Yes, I know time theta 2, let me put it e to the power of minus s tau d here. This will become theta. Please see theta 2, between theta 2 and theta I am putting another transfer function e to the power of minus s tau d, and therefore, the total model from this point to this point as you see is given by e to the power of minus s tau d over tau s plus 1. This, the concluding statement for today's problem I am giving, that this transportation lag or dead time is a problem for the control designer. It creates instability problems, and the control designer has to account for the problem introduced by transportation lag in its control system design. Okay. We will come to these problems, but in the modeling exercise, whenever there is a transportation lag, I will like to model that situation by a block of this form e to the power of minus s tau d, where tau d is the dead time. Thank you very much.